Good morning. We are on at the end of section 11.1. That's where we start. So I think we stop where we brought the remainder theorem. I mean, not the remainder theorem, but the remainder of the Taylor theorem. Now we continue with the example. So we try to find the Taylor polynomial to estimate this function centered at x equal to 0. So pretty much what we did is this table, and of course we will do this a lot in this chapter. And then we have up to n equal to 6. So we're going to need on the way to 6. That's okay. Right, and then on the top first we will have the derivative of the k order x, and then we evaluate that derivative at the point, and then finally we divide by the k factorial. Right, so that's simple enough. So first x equal to 0. So that's what A is. The center of the Taylor polynomial. So it should be very simple. So first we'll have the function is e to the x, and then we evaluate at this point. And that is 1. And then next we will take that, divide by the factorial of that number. 0 factorial is 1, and we have 1. Next, first, that will be the first derivative. Luckily on this one we just have e to the x, so all of them derivative is just e to the x, and all of these two columns will be consistently the same thing, pretty much. Derivative when x equal to 0. And so that's just 1 over 1 is still 1. And we'll keep doing that. And x equal to 2, that is the second, when k equal to 2, that is the second derivative, is the same thing. So and we'll take that, divide by factorial of 2. 2 factorial is 2 times 1, which is 2. Just 1/2. 2 times 1. And we'll just keep doing that. And then we take that number, divide by factorial of 3. Be 1 over 3 times 2 times 1, 1 over 6. And keep doing that. Now 4 factorial, we're not going to write 4 slash, but just use 4. And derivative still e to the x, and the values are still 1. And we'll take that, divide by 4 factorial. 4, 3, 2, 1. And 1 over 24, and then 5. So from just 1, so that's very simple. 5 factorial is 5, 4, 3, 2, 1. 120, and then 6. And it's also 1. Polynomial. So we estimate the function e to the x is approximately equal to. Right, I'm just going to write this in the general form. First we have the values at a. Next we have the derivative at a, and then seeing the center at a, we have x minus a, and then second derivative over 2 factorial, and then x minus a square, and then the third derivative, 3 factorial, and then the power to the 3. So derivative, the power, and the factorial, all of them have the same number, and a in this case is 0, so we just have x. Instead of x minus 0, or just x. So in this particular, we start with 1. That f of a, that's it. And then the derivative also 1. And then x minus 0, just x. Then second derivative is 1 over 2 factorial. Actually, we have that is 1/2. And then x square. And then 1/6. X minus a, so just x cubed. The coefficient 1 over 24, x to the 4th, 1 over 120, x to the 5th, and 1 over 720, x to the 6th. Here, just put dot here. So because that just keep on going. Here also the same. Just keep on going. Right, so we have that. Now, the question also asks us estimate the error approximating e to the 0.45. So first, we need to, by the way, this is a polynomial of order 6. So we're going to say polynomial of order 6 of x. Now, just need to evaluate this as 0.45. So for this, I'll use the calculator because I'm not going to do all of that. And the best way to do is to store this number into x. So 0.45 store into x. And then we evaluate this. I'm just going to say 1 plus x plus 1/2, which is 0.05, x squared plus 1 over 6. If you want to be nice, have a fraction. X cubed (1 over 24) x to the 4th (1 over 120) x to the 5th and 1 over 720 x to the 6th. So we have that 1.5683114. Right, so that is the estimate values. Store this into x and evaluate that polynomial, and this is an approximation. Now we find the actual values. The actual values is just e to the 0.45. So we're just going to type that e to the 0.45. We have that 1.568312185, and we just subtract this 2, and that is the error. So the 6 subtract and take the absolute values. So pretty much we have this number, subtract that number. Just highlight, hit enter, and that like copy and paste, and we have 7.85 times 10 to the negative 7. By the way, because we have absolute values, so that negative answer will turn to positive. Now let's see if we can have more decimal numbers than this. So in this case, let's see, we have a few more. Can we have that? Like 5 decimal places. Now, just keep that. By the way, if we go to scientific notation or engineering notation, what's different? Usually scientific notation is this, but engineering, they will give us in the multiple of 3, I think, like -9, -3, -6, or 3, 6, 9, so on. Let's see. Yeah, so just give us in the multiple of 3. I get back to normal. Right, so pretty much this. Like I said, I should be able to do this. This is the simplest example, because all of them are e to the x. Sometimes it's more complicated. It just depends on what function we have, and the derivative could get more complicated. Right, so that is Taylor polynomial. Later on we call that is the Taylor series. In this particular Maclaurin series. Right, with that we go to section 11.2. This is properties of power series. One is on the special case, we have a geometric series. Right, first of all, what's so special about it? Well, let me go way back to page 86. Right. So if we go to section 10.8, when we learn about all of the convergent tests, and you see all of these tests, they only tell us if it is convergent or divergent, and did not tell us what is the sum, except for the geometric series we do have the series equal to some values, so that's why it is special. For the series we have the actual values equal to something. That is for the geometric series we know the sum. So that's why it is special. It has the values of the series. First, recall that for a fixed number R. We have the sum of the powers, just 1 plus R squared all the way to, and it will be equal to 1 over 1 minus R. and that of course very important. The ratio has to be between -1 and 1, or we say the absolute values. Oh, sorry, I didn't see the question. This is going to be positive because we have absolute values. In the calculator we have negative, but because of absolute values it is positive. Sorry, didn't read the question until now. Right, so we have that. Should pay attention more. Right, now if we replace to a power series, now instead of a fixed number R, we replace that into an X, which is a variable. Now replace R by variable X. Then we have the same thing. Instead of R, we will have X. The index though is still K. Now we have X to the K. And we still have 1 over 1 minus X. And we still have X between -1 and 1, or absolute value of X less than 1. Oops. And the difference, if you go back to all of the geometric all the tests, they would never have X in it. Sorry. As you see, on all of these tests, none of them have X in it. They just have K as the index. No X here. The power series, the difference is that we will have X as the variable in it. Right. And if we have X, in this case we say X, absolute value of X less than 1, that gives us the interval from -1 to 1 as the interval of convergence. The set of values for which a power series converge is called interval of convergence. Right. Now we go to the power series. First definition. Right, a power series. I'm not going to write everything, or that's like bit much. So when we have K go to 0 to infinity, that is the index. We'll have the coefficient C of K, and X minus A to the K, and C of K is the coefficient and A is the center. and A is the center of the power series. And in that case, the set of all the x for which the series converge is the interval convergence. So up to this point, if you ask, well, what's the big deal about convergence? Convergence is pretty much is where the series has the values when it equal to a finite number and not infinity and not undefined. So if this equal to a number, then it is convergent. It could be, that number could be anything between and it's not infinity and not undefined. So now when we talk about this, it is only on an interval of convergence, because we talk about the line number. We might have something, the power series will have a center at A, for example, and the interval of convergence will usually be between two numbers, just like this, between -1 and 1. So instead of write like that, we can also write x between 1, -1, between -1 and 1. So if we have the whole interval convergence, will be that much, then each one of this the distance are called the radius of convergence. Which is from the center to the edge of the interval of convergence. Right. Now, that's why when we have the center of the power series, that is the big deal, because it does have from that center to the outside of the interval, that those should be the same number. Next, we have a definition. It says that there will be three cases of intervals of convergence. So a power series and that obviously center at 8. Converges in one of the following. So there will be three cases of convergence. The first is convergent for everywhere, convergent everywhere. Convergent for all x. In that case, interval convergence is negative infinity to infinity, and the radius of convergence equal to infinity. That's the first case. The second, there exists a number R so that the series converge 4. So I'm not going to write everything like that. So they said there will be excess or positive such that x minus a less than r. So in which case interval convergence is so in that case this will be converge. Let's say convergent, and if it is more than that, it will be divergent. And radius of conversion is equal to r. Sorry. Radius of convergence is r. Let me try to draw this in a better way. Right. First we have the center, and then we have the radius, from the center. In that case, we have the edge, and of course this is a minus r and a plus r, not d, is a minus r, a plus r, and it is convergent interval of convergence. We're going to say x minus a will be anywhere within those points less than r or between those 2 points. However, here's a tricky part. So if it is between those interval, it is interval convergent will be in between. It is divergent if it is outside for sure. So the series diverge if the number is on the outside. So that for sure we know that the only thing happened is what happened at the boundary. So that's a little note. Need to check what happened when this is equal to. We have on the outside, we have on the inside, we just don't know what on the boundary. So usually we need to check for boundary. At this 2 points. And so there to be 3 cases. First, the radius is equal to infinity. Next, is equal to positive. And then last, it is equal to 0. The series may be just converges at A, in which case r equal to 0. So there will be 3 scenarios. The radius of convergence, infinity, a constant, a positive, or a 0. So 0, infinity, or constant, or positive constant. Right. Now let's see how that works. Let's go to examples. Find the radius of convergence. Find the radius of convergence. And interval of convergence. So we'll find 2 things, radius of convergence and interval convergence for this series. The first one we have is x to the k and then k factorial. So the difference here is that we not just have k as the index or something that change, also have x. So how do we do this? Right. So of course for here we have to check, make sure that the series is convergent. So there's a bunch of tests. So in 10.8 we have a bunch of tests, 9 of them in particular, and so we have to choose one test that will work. Right. So yeah, we really not take the limit when k go to 0. So the divergent test doesn't work here because we don't know what x is. What we can do though is use some of the convergent tests, and when I see the power of k or factorial, this one has factorial for sure, that's where we use the ratio test. So most of this we use the ratio test. For ratio test, we will let a of k, the term be that. Right. The ratio test is we will let r equal to the limit as k goes to infinity, absolute values of a of k, which one? It's a of k plus 1 over a of k, right? So That is the ratio. If that are less than 1, convergent, equal to 1, inconclusive, greater than 1, divergent. So that's why when equal to 1, it is inconclusive. Wait, okay, inconclusive. So that's why we need to check the boundary, because that when it is equal to 1, we don't know what will happen. Right, so we do that. X to the k over k factorial. Now if we have k plus 1 instead, so we're going to have k plus 1 here, k plus 1 here, and k plus 1 here. So we have x of k plus 1 over k plus 1 factorial. And at the bottom we just have x to the k and then k factorial. The ratio of that so divide fraction is multiplied reciprocal. Right, now the power we can split to x to the k plus 1 is x to the k times x to the first, and k plus 1 factorial is k plus 1 times k factorial. And usually in the ratio test there will be a lot to cancel out. K factorial cancel out, x to the k cancel out. So we just have x over k plus 1, absolute values of that. Right. And we have the ratio is equal to 1 if it is less than 1 if it is convergent. So that R have to be less than 1 for the series. Have to be that for the series to be convergent. Right, so what happened? Now notice since k goes to infinity, as long as x is finite, a finite divided by infinity will be equal to 0 and therefore less than 1. So I will write a little note here. Note, since we have the finite divided by infinity and the bottom we do have infinity, right? Because k go to infinity. Because of that, we have x over k plus 1 will be less than 1, will be equal to 0, and if it is equal to 0 certainly will be less than 1 if x is finite. Right? Of course, if x go to infinity, infinity over infinity is indeterminate. We don't know what happened. But if it is finite, then finite divided by infinity is 0, and 0 of course is less than 1. So when x is finite, meaning usually when we say finite, we say x between infinity, negative infinity and infinity. Because of that, we have the radius of convergence. Or equal to infinity, and interval of convergence will be from negative infinity to infinity. Right, so that is the first case. We will find the radius of convergence and then interval convergence. Right. Number 2, this is the longest one, so I'm going to save that for after the break. Let's just go to number 3 first. Right, now we have k factorial and then x to the k. So we still have a power series, and now we just need to find what values of x will make this convergence. So as always, we use the, and for this kind of test, we use the ratio test. And we still let a sub k equal to that. So we'll take the ratio. Right. First we're going to put k plus 1 into k here. So we have k plus 1 factorial and x to k plus 1. And at the bottom, a sub k will be the same thing. Right. And then in this case we don't need to flip the denominator, just have that. So we have k plus 1 factorial k plus 1 times k factorial. Next to the k plus 1 is x to the k, x to the first. I don't really need that much. And k factorial x to the k. Right, that's simplifying. X to the k cancel out, k factorial cancel out, and what's left is just k plus 1 and then x. By the way, since k go to infinity, k certainly is positive, so we can just say like that. this have to be less than 1 for the series to converge. But notice that because we have k plus 1 here and k goes to infinity, so if x is equal to any numbers, this will not happen. Since k goes to infinity, k plus 1 certainly goes to infinity as well. So if x not equal to 0, then k plus 1 times x would go to infinity, or could be negative as well. So think about it. If x is very small number like 0.01 times infinity, of course still infinity, but x could be very small but negative number. When time infinity will be negative infinity. So doesn't matter how small the number is, if it is constant multiplied to infinity, it will be infinity. So in that case, the only thing that make it less than 1 is that x has to be 0, because 0 times infinity is indeterminate. Why did you put k here? Oh, k, first of all, let's talk about factorial. K factorial is going to be k times k minus 1, k minus 2, and all the way to 1. Now, in that case, we can decide to stop. Let's say we stop at here. That, of course, is k minus 3 factorial. So we can have k times k minus 1, k minus 2, and k minus 3. If we don't want to write anymore, we just say factorial. So this means factorial means that just keep going in until 1. So now to the case of k plus 1 factorial. For k plus 1 factorial, meaning that we start from k plus 1 and the product, we have the factors of k plus 1 and then k minus 1, just 1 less than that until we reach 1. And note that by definition, from k all the way back to 1 is defined to be k factorial. So we just have k plus 1 times k factorial. So that is k plus 1 factorial. Right? Yeah, so that's k plus 1 factorial, k plus 1, and then k factorial. If we want to, we can also write k plus 1 factorial is k plus 1 times k minus 1 factorial. The nice thing about factorial is we can stop at any factor we want. Just put the exclamation point there and factorial, which that we mean we go from that number all the way back to 1. Right? So that's what we have. Right. So we say if x not equal to 0, then that go to positive negative infinity. So the only case that is not the case, if x equal to 0, then k plus 1 times x is equal to 0, and that's it. And if it is equal to 0, so it will be convergent. Equal to 0, meaning less than 1, which will be converged. Yeah. So for this problem, the radius of convergence is equal to 0, because it only convergent at one point. And the interval convergence is just one point. It's just a point, 0. Right, it's 9 o'clock, so I think we'll take a break here. We continue at 9:06. Be back. By the way, you should have an email that I sent a few hours ago. I said about what part of the note you need to send back, and there are 10 of them. So if you have any question on that, just send me an email, or you can ask during class. And by the way, probably because of that, yeah, I meant to wait until later to ask for the note, but I just want to have everything done during this week, so you can prepare for the final next week. Yeah, just want to get that out of the way. And also, I'm not sure if I post the review for test 3 yet. Let me check. Nope. Just post the test we review. Right. Now we'll go back to second example. This one will be a bit longer than the other two. So we find the radius of convergence and interval convergence for this series. Once again, we use the ratio test. So usually when we're trying to find the radius of convergence or interval convergence, we use the ratio test. So in that case, let's A sub k be that term. And then we find the ratio R. Ratio of the next term over this term when k goes to infinity. So we have that, but with k plus 1. Sorry, plus 1. Sorry, should be that. K plus 1, K plus 1, K plus 1. No factorial here, alright. Now then we just have that. Right. We have this -1 to the k plus 1 x minus 2 k plus 1 over 4 power of k plus 1 times divide fraction is multiplied reciprocal. Right, Now the k plus 1, k plus 1, k plus 1, we need to split to cancel as much as possible with this. Negative 1 to the k, negative 1 to the first, why not? X minus 2 to the k, x minus 2 to the first, 4 to the k, 4 to the first, or just 4. This will just have 4 to the k, negative 1 to the k, and x minus 2 to the k. Right, now try to simplify. 4 to the k cancel out. Negative 1 to the k cancel out. And x plus 2 to the k cancel out. So what's left? X minus 2, negative 1, and 4. Negative x minus 2 and then 4. Right, so that's what's left. Simple enough, right? By the way, since we have absolute values, absolute value of 3 is the same as absolute values of 3. So in that case, this might be positive or negative, doesn't matter. We just take that away. Absolute value will guarantee the whole thing will be positive. I just dropped the negative because the negative there or not doesn't matter. We have absolute values anyway. And talk about that. If it is a positive number, then we really don't need to put absolute values around the 4, right? Because 4 is positive already. Don't need absolute values. Or absolute values doesn't do anything to it. So we have this. And that's just like the last one. We need this to be less than 1 for the series. By the way, there's no k in here, right? Doesn't matter what k is. It's always that. So that will be the limit. And finally, we need this to be less than 4, less than 1 for the series to converge. And so we just multiply 4 on both sides. And we have that. And now when we write like that, the 2 obviously is the center of the power series. And 4 in this case will be the radius of convergence. So the radius of convergence. So let's draw a number line here. We have 2 at the center. If we go 4 units on one side and 4 units to the other side, that have to be 6, right? If we go 4 the other way, this have to be minus 2. Because 2 plus 4 is 6, and 2 minus 4 is negative 2. So 4 away from 2, we have 6, and then negative 2. Right, now it's not that difficult up to this point. Right, now we'll go back to the notes. It says that usually we need to check the boundaries. When we have this, we know that inside of negative 2 and 6 it will be convergence. Outside of that it's going to be divergence. But what happened at negative 2 and 6? So we do need to check the boundary. If the question only asks us for the radius of convergence, then we say 4 is the radius convergence, or we say the radius convergent is equal to 4. That's it. But if it asks for the interval convergence, then we need to check the boundary, and that will be a lot more work than this. So for boundary, we're going to use 6, and then we use negative 2. First, for x equal to 6, I'm going to put 6 here, minus 2 to the k, 4 to the k, negative 1 to the k though, sorry. I'll keep doing that. Right, so this is k equal to 0, negative 1 to the k, and that is 4 to the k. Right, 6 minus 2 is 4, and then in this case we cancel out, and it is just this. Right. And my question is this one convergent or divergence? Yeah, just multiply 4 on both sides here. Yeah, and the way we write the radius convergence, yeah, if it is in this form, then the radius convergence is x minus the center less than the radius. Yeah, so when we write that form, then we say the radius convergence is 4. Right, now what's that series? Is that convergent or divergence? So we don't even need to have any test, just have a good reasoning skill, and that should be it up. So negative 1 to the k, when k equal to 0, negative 1 to 0 power is 1. When k equal to 1, so pretty much we just have plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. And if this one go indefinitely, which no, it's negative x minus 2, and actually all the k cancel out here. Yeah, so 4 to the k cancel with 4 to the k, because there's no factorial here. If there's factorial, yes, there will be a k here, but because that is 4 to the k, so all the power we cancel out and we just have that. There's no k here, no case in here to substitute in. Yeah. If there's a k here, then yes, there will be k somewhere after that. But since there's no k here, no k there to substitute infinity in, so that's all we have. Oh, I haven't get there yet. Now we just put 6 in first. Yeah. Now we let x equal to 6, and then later on we'll check x equal to -2. Yeah, I'm not getting there yet. I'm just do 6 first, and then we'll go to -2. Yes, definitely that will be -4. Yes, but that will be next. So -1 raised to the k, and we know that if it is just 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, the series will be divergent because we do not have a fixed number. So the sum is just going to be 0, 1, -1, and then just between those values. So by the divergent test, this one diverge. Right. Since the last term not equal to 0, so the series divergent. And we use divergent test. If the last term does not go to 0, it cannot converge because the sum keeps changing. Right, that is x equal to 6, divergence. Now how about x equal to -2? Now we do need to substitute both boundary points. Now we have -2 to the k. Right. Now we have -1 to the k power, and then -4 to the k power, all over 4 to the k. It's not a form, don't worry. So -1 and -4, both of them under k power, so actually we can bring everything inside the k. We don't need to do that, just do that for the top. Just bring the negative and then the -4, all of them inside k, right? I just combine this, -1 times -4, both of them bring inside the k power. -1 times -4 is just 4. Which cancel out. Just have 1. Now that one we don't even need to use any test, just a common sense. K equal to 0 to infinity, meaning that this one equal to 1 plus 1 plus 1 all the way to infinity. And if we just keep adding like that, it will be infinity, which is divergence. So what we have is between -2 and 6 convergent, at the boundary divergence. So interval of convergence. Interval of convergence will be from -2 to 6, or we write x between -2 and 6, not including the 2 and -2 and the 6. So that's why we need to check boundary. If the boundary is convergent, we make it equal to, if that is the case. But in this case, both of them divergent, so we do not have the equal sign on the -2 and 6. Guarantee some one of the homework problem or on the test review, we have the equal sign on one of them. So that's why we always have to check boundary. When the radius of convergence is a constant, we need to check for boundaries. Right, so that is that. So use the ratio test, and that should give us the radius convergence. And then if it is a finite number, check the boundary. Maybe one boundary, make it convergent. In that case, make it equal sign. In this case, none of them works, so no equal sign. Yeah, I remember one of the test review question, it has the equal sign on one side. So I will do the review this weekend, and so we have that example when we have it. All right. Now we could go to the next part of the power series. Number 3. Working with power series. Theorem. It's back now. Right, I just hit refresh. Should working now. Right, I actually connect directly to the modem with the cable. If it doesn't work, I have no more solution. But it's much better. I mean. Yeah, it will be less of a problem than the first few days. So I have to use the cable. Actually, it shows when there's rough frames, but I sometimes didn't pay attention to a lot of things. So sometimes didn't pay attention to that. So, what I was saying is that we see this a lot. Almost in everything about limit, derivative, integral, and now the sum. So, the sum, the series of a sum equal to the sum of the series. So, and then the multiplication if we have x to the m multiplied to the power series, then we just multiply then and when we multiply we can add the exponents. And it also say that this will be convergent. For x in that interval I. And number 3, convergence. If we have h of x equal to bx to the m, m is a positive integer, and b is the real numbers. Then we have that converge to that for all x such that h of x in I. So I'm just going to write that out, but meaning that when we substitute into x of the power series, we can substitute a function into x. So in this case, not just x, sometimes it could be a function as well. Right. Now we go to example. Find the power series for the following. Before we do that, let's just look at one important thing. That is what we learned from the beginning of the section. That is the power series. So if we have that, then that equal to 1 over x, and that convergent between when x is between -1 and 1. So it will be very useful if we know this. So 1 over 1 minus x equal to 1 plus x squared if absolute of x less than 1. So we need to use that. Now we have a problem. X to the 5th 1 minus x. So what's that equal to? Right. Now, this actually, now it's bad. All we can say is move the x to the 5th to the back. right? And now we write that. Now I'm going to write this is that. And now we just multiply x to the 5th. By the way, when we write like that, it only works if absolute value of x less than 1. Yeah. Otherwise, we cannot write the sum like this. And then we just multiply it out. That should be simple. X to the 5th, x to the 6th, x to the 7, and increasing. So simple enough, right? So you realize the fact that 1 over 1 minus x is the geometric series which equal to the sum of all the power of x. Simple enough, right? Next, by the way, I will change the problem here. Instead of 1 minus 2x, I will change the 1 to something else. So make it a little more complicated. Instead of 1 minus 2x, let's use 3 minus 2x, and then change the problem to 3. So make things a little more complicated. So again, the only power series we can have, we can utilize is this one. So somehow we have to turn into 1 and then 1 minus x. In that case, we can write that as a power series. So how do we do that? First, we have 1 on the top. That's not really important. What's more important, this is, it has to be 1. So the 3 there needs to be 1. So that's why I change this problem to something else. Because if it is 1, it's too easy. Try to change to something more complicated. Because on the test, you might see something like that. So that 3 need to be 1. So we need 1 minus something. So in order to get back to 1, what we do is multiply 1/3 on the top and 1/3 at the bottom. So we have 1 over 3 on the top. At the bottom, 1/3 times 3 is 1. And then 2x times 1/3 is 2 over 3x. Right? So it has the form of that. 1 minus something. The top doesn't matter. We can always take that to the back. Can always move the 1/3 to the back and have 1 on the top, and just put the parentheses around this. So we do have 1 minus something in that case. So with that, we can write the power series for this one. So for that power series, x here is replaced by 2 over 3x. So we're going to have 1 plus negative 2 over 3x plus negative 2 over 3 x squared negative 2 over 3 x cubed, and so on, and then multiply by 1/3. And don't forget that when you write like that, 2 over 3x, I forgot. It only works if we have 2 over 3x less than 1. So that power series only works if there's some certain interval for it, or we call the interval of convergence. Right. The powers, if it is even, is positive. If it's odd, it's negative. So we have 1 minus 2 over 3x plus 2 over 3 square, negative square is positive, 2 square is 4 over 9 x square, and then minus 8 over 27 x cubed, and then so on. So you will see that the size alternating, and then times 1 over 3 on the back, which multiply 1/3 to it. 1 over 3 minus 1 over 3 times that, 2 over 9, 4 over 27, 8 over 27, 81, right? And note that we have the condition there. So if, only if we have 2 times 3x less than 1. If we want to show it further, we take the 2/3 outside of absolute value of x and multiply reciprocal. So x less than 3/2. So this is the interval convergence, and that formula only works if x, absolute value of x, is less than 3/2. So that's why I changed it to 3. So because we do need to change it back to 1, so I try to change that to something else. Because the form is always 1 over 1 minus something. Even though if it is x squared like this, we can always change to that, right? Negative is positive, and we always have to write 1 over 1 minus something, and that is equal to 1 plus that something and that's something square and that's something cube. Just keep doing that, and once again, whatever that something is, have to be less than 1 for it to be convergent. Right, I'll just do it. 1 minus x squared plus x to the 4th minus x to the 6th. So that is the power series, and this is only if x squared less than 1. So meaning x is between -1 and 1. Take the square root on both sides, and we have between -1 and 1. So utilize that geometric series. Right, next, carve different things. Earlier saying that we can combine the series. Now, not only we can combine them, we can do some calculus on it, meaning we can take derivative and we can integrate. Be defined by the power series. Ck x minus a to the k on the interval of convergence. If it has the power series representation, then the function is continuous. Again, if it has the series representation and that series is convergent, the function is continuous. And next, we can integrate and differentiate the series term by term. And when we do that, we will have the following. Now, let f of x equal to c of k x minus a to the k. The index here, I'll worry about that later. If that is the case, then when we take derivative, just take derivative of this. Bring down the k, right? And then we have x minus a to the k minus 1. And then we can integrate. X minus a to the k plus 1 over k plus 1. Let's see. So we just integrate term by term. And all the power series will have the same interval convergence. Let's see how it works. So it says that we can take derivative term by term and integrate term by term. Differentiate and integrate the power series. Let's say we have this series f of x equal to 1 over 1 minus x. And because we know that series is equal to 8k equal to 0 to infinity of x to the k, which when we write out 1 plus x squared plus x cubed plus dot dot dot. So how do we differentiate this? Right, we take derivative. Of course, we can take derivative of all of them, but now focus on the power series. What is the derivative of that? Derivative of 1, 0, derivative of x is 1, derivative of x squared, 2x, x cubed, 2x squared, and so on. So we will write as 1 plus 2x plus 3x squared. But how do we put that in a summation though? Right, so note that the number increasing, right? 1, 2, 3, and so on. So the first one is 1. So if we let k equal to 1 to infinity, then the coefficient is going to be k. And then we have x. The power of x though is 1 less than the coefficient. So yeah, that's what we have. And that's all we have. Right. So if we do term by terms, that's what we have. Now if we do directly, just going to take derivative directly of the series, then we're going to have the sum derivative directly like this. When we take derivative, bring down the k and xk minus 1. Yeah. Right. However, for this series, when k equal to 0, 0 times anything is 0. So this is equal to let me write like this instead. So now we're going to put 0 in for k, step 0, and then x to the k minus 1. So if we put 0 in for k, 0 minus 1, and k 0 times anything is 0, and after that the series will pick up from 1 to infinity. Okay, x to a k minus 1, and either way we have the same answer. Right? So that's when we take derivative. just do term by term. So we can do individual terms or just integrate for the term right on the sequence. Right, now what is integral? So now let's just do that to the series. We can just integrate, bring the integral inside the series. And integrate of x to the k is x to the k plus 1 over k plus 1, and then plus a constant c. And then that constant c actually for each one of them and for all of them, so it doesn't matter. The constant c here is outside of the sum though. Yeah, because when integrate we only need one constant at the end, so that is the summation. The constant c is not inside the summation. Right, so just integrate term by term. Again, if we want to, we can write a bunch of terms and then we differentiate or integrate, or we just do that directly into the terms of the sequence or of the series, and that's still the same thing. Right, take 5-minute break. We'll continue at 10:05. I got the email from yesterday, and the news today. It says that Dallas County Community College will go online for most of the classes in the fall as well. So we're going to be online for a while. For math like this is probably not as bad, but I'm not sure how to do chemistry or physics or biology online. That's gonna be tough. Wait. Right. Next, use the fact that integral is equal to that. I'll write the power series for tangent inverse of x. Right. First, we're going to write the power series for inside, for that part, and we already did that, right? Yeah, equal to this. So first, for that one equal to and we can write the power series 1 minus 1 plus negative x squared plus negative x squared negative x squared cubed, and so on. If we write that as a power series, it will be negative x squared to the k power, go from 0 to infinity. Right? So if we need to integrate this function, we can integrate the series. By the way, let's just rewrite this as now, just write like that. If we want to rewrite this, we can write negative 1 to the second. Sorry, there's no power here. And then x squared, we just separate them all of them under the power of k. Right, that. Right? -1 times x squared, and then -1 to the k power. And then x squared to the k power. X to the 2k. Right. That is better. Just to keep that. Now, instead of integrate this, we can integrate the whole series. So integrate the whole series. To integrate the series, we can just integrate the terms in the series. Right. And notice -1 to the k, doesn't matter what it is, it's still constant because there's no x in it. So take that out. And the integral. And then we have the integral. It's only x to the 2k dx. Right. Now, and -1 to the k. Integral of x to the 2k is x to the 2k plus 1 over 2k plus 1 plus a constant c. And the integral of that one, according to the problem given, that one is equal to tangent inverse x, let's say plus c. But usually we just need a constant. We move one constant to the other constant. Those two constants are not the same, so I'm not going to cancel the constant because they're not the same. But we can move one to the other and combine them. So pretty much we just need a constant on one side. I'll just keep on that side. Right, so we just need the constant on one side, because we just move one to the other side, and a constant plus a constant is still a constant. Right, so that's good and all, but I'll just need to solve for k. So for c, the constant. Of course, when we write like this, that term have to be less, absolute values of that have to be less than 1 for this to be convergent. Talk about that later. But for now, how do we solve for c? So, now if I just put 0 in for x, let's see what happened. What happened at x equal to 0? We have tangent inverse of 0 plus a constant equal to that. Now we're going to put 0 in 2 to the k plus 1 over 2k plus 1. Now 0 times anything is 0. So that's why we just have 0. By the way, what is tangent inverse of 0? That is 0. So we have 0 plus c is equal to 0. So obviously, c is equal to 0. If c equal to 0, tangent inverse is equal to that. Because of that, that's a little off. Because c equal to 0, we have tangent inverse. Equal to -1 to the k x to the 2k plus 1 over 2k plus 1. So we just have that. Right, so that's the end of the problem. Now just want to bring this interesting fact into this. Now, actually the problem is done. Now this has the historical purpose into this problem. So what we do now is let x be 1. Could put 1 in this series. Tangent inverse of 1 equal to this series. One raised to any power, still 1. So we have tangent inverse of 1 equal to this whole thing equal to 1. So we just have -1 to the k 1 over 2k plus 1. Right. So how is that significant? So let's just say what is tangent inverse of 1? I will keep this in degree mode. Tangent inverse of 1 is 45 degrees, which is pi over 4. And this series, I'm going to just use some, just write this series for a moment. And we'll just multiply 4 on both sides. So we have pi equal to 4 times that. Now, if we want to write a few more terms, when k equal to 0, we have 1 over 1. When k equal to 1, 1 over 3. K equal to 2, 1 over 5. K equal to 3, 1 over 7. So you get the idea of how this series goes. whatever that series equal to, multiply by 4, it's going to give us pi. So that is extremely useful. So that is the way to estimate pi. Actually, historically there's a bunch of different ways to get pi. The calculator, of course, give us that pi values. But if we want in terms of summation, let's say we do this. X equal to 1, oops. Instead of k, I use x. Go from 0 to, let's say, we use 100 terms. -1 to the k power. And then times 1 over 2k plus 1. Right. Let's say if we add 100 terms of this, and at the end we multiply by 4. What do we get? Right. Well, as you see, we get the number that is close to pi. So the point here is we have that, and we write that as a series. Now integrate the whole thing is like integrate the terms of the series. So we just integrate the term of the series, and then at the end we solve for c when c equal to 0, and that's pretty much it. That's the end of the problem. This part has the significant historically important, because that's the way to estimate pi. But the point here is we can integrate term by term, or we can differentiate term by term. Just like the last problem, when we integrate every term in the sequence, we just integrate that, and that's it. Just integral, and has k in it. K is a constant. Go to next section. So the later part might be a bit confusing, but bottom line is, if you can write that as a power series. Now, writing from here to here, yes, that sometimes it's difficult to come up with the series, even though we have a bunch of terms. I mean, from here to here, yeah, that could be a problem. Right. Yeah, to just check derivative and integral term by term. That's fine. Taylor series. Now we get back to the series that we've been doing using this table. So now we're going to do a lot of this table. 1. Definition. Suppose the function f has derivative of all orders on an interval containing the point A. Then the Taylor series Now we don't call the Taylor polynomial anymore, we call that the Taylor series, but still the same thing. For f center at A is f of A plus derivative at A x minus A plus second derivative at A over 2 factorial x minus A square, third derivative over 3 factorial x minus A cubed. So pretty much the order of derivative, the factorial, and the power of x minus A, all of them must be the same number. And we can put as a summation k equal to 0 to infinity f of the n order derivative at A over n factorial, and then x minus A to the n. Yeah, I should be able to still see it, all the formulas over there. Now when A equal to 0, the series is called Maclaurin series. So when it's center at 0, it's called a Maclaurin series. Right, 2. It doesn't matter though. But if we use all the n, so let's use n. Yeah. Back in Gauss algebra or pre-calculus, the index usually we use I, right? Because I stands for index, so we usually use I. But when we go to later on, when we have engineering and high level, we don't want to use I because I is confused with the imaginary I. So the engineering usually they use J. But I just don't want J because when we write J, it's sometimes too confused with one or confused with I. So that's why we write K or N or more distinctive that way. So interchange between N and K, it doesn't matter. It's called the index. So could take anything. Yeah, thanks. Yeah, so that could be. Yeah. In the formula have K, here we have N. Doesn't really matter. Right. Now we have a sample. Now we'll go back to the series. Like I said, the most important things that the last thing I want you to forget about this chapter is how to do a table like this and find the Taylor series. Example 1. Find the Maclaurin series. Well, Maclaurin series is a Taylor series, center 0. First we have the function is cosine of x, and this time center is 0, or we call the Maclaurin series. So just make this table, and of course that we use this a lot. So make sure you remember how to do this. Alright, for this one we need to go from 0. Of course we can always go down and have more terms on the table and more terms in the sequence, but this time let's go from 1 to 4. Shouldn't draw this with the ruler, really, with the pen, I mean. Right. Right, so we did plenty of this. First, we have the the k order derivative, and then the k order derivative at the point A. In this particular, from center 0, so A equal to 0. And then we're going to have that over k factorial. That gives us the coefficient. Right, now just do it. Now the function is equal to cosine of x, and then we evaluate cosine of 0. Cosine of 0 is 1, and we take that divide by factorial of 0, which is 1, so we have 1. Next we take derivative. Derivative of cosine is negative sine, and then we put 0 in for x, which is negative 1. Sorry. Sine of 0 is 0, so this is remaining 0, and over factorial of that. And then we'll take the derivative. Derivative of sine is cosine, but they're still negative. Negative cosine, and then we put 0 for x. This is negative 1. And we take that number, divide by factorial of 2. 2 times 1, so negative 1/2. And then we take the third derivative. Derivative of cosine is negative sine, so I have negative sine, which turn out to be positive sine, and sine, substitute 0 for x, and we have 0 over factorial of that number, 3 factorial 3 to 1, which is 6. Doesn't matter though, 0 divided by anything is 0. And then the fourth derivative. The reason that we have to go up to 4 because we have 1 give us 0, 3 give us 0. We only have 2 terms, so we need a little more than few terms. Derivative of sine is cosine. We have 1 over 4 factorial. 4, 3, 2, 1. And you have that. And then put all of that together, we can say cosine of x equal to 1 plus 0, I just say plus 0 x minus 0 to the first minus 1/2 x minus 0 to the second plus 0 x minus 0 cube plus 1 over 24 x minus 0 to the fourth. Right, which equal to 1 minus 1/2 x squared plus 1 over 24 x to the fourth, and then minus. But now let's go back. Instead of do this, we can write 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth minus, if we keep going, it will be 6 factorial x to the 6th. And if we put things together into a power series, we only have x to the 2k over 2k factorial, because the reason is 2k because all of them have to be even. Now, if you remember back in trigonometry or pre-calculus, that is the Taylor series. A is equal to 0, so x minus 0. That's why x minus a is. Yeah, so always write x minus a, and a this time is equal to 0, so just have x minus 0. Right, now back to pre-calculus or trigonometry. We know that cosine is an even function. Now we see that y, all of them are even terms, even power of x, so that's why it is an even function. And in here we have x to an even number divided by factorial of an even number, and we have the negative 1 to the k plus 1. This, so the sign will change from positive to negative. Right. Let's keep that for now. Right. Next. I guess we have to do that. Right. By the way, what do you think this equal to? Without doing anything, Remember, this is a geometric series. So that equal to that. But we're going to make a table the same way. I just use pencil. In that case, we can erase. Want to make a mess. Let's use another one then. K 0, 1, 2, yeah, the 3 times, up to 3. Right, so have k and then the k derivative at x, k derivative at a, in this case is Maclaurin series, so a equal to 0, and then that over k factorial. Right, so first the function put 1 in for x, I mean put 0 in for x, 1 over 0 factorial 1. Next we take derivative. I will write this as 1 minus x to the negative 1. So the derivative of that is negative 1 minus x to negative 2, and then derivative of the parentheses, derivative of that is negative 1. Negative and negative, 1 minus x squared minus x to the negative 2. Right, and put 0 in for it. H is 1. 1 over 1 factorial equal to 1. Second derivative, take out the negative 2, that will becomes negative 3, and then we have derivative of 1 minus x, which is negative 1, as we had before. So negative and negative, so that is the 2, 1 minus x to negative 3. So 2, 1 minus 0, 2 minus 3. 1 to, I mean, that's 1 to negative 3. So 1 times 2 is 2. 2 over 2 factorial, also 1. And then the third derivative, take the negative 3 down, that's negative 6. And then derivative of 1 minus x, which is negative 1. So give us 6, 1 minus x to the negative 4. So that is still 6, and 6 over 3 factorial, 3, 2, 1 is also 1. So keep doing that, and all the coefficient will be 1, and therefore 1 over 1 minus x equal to 1 plus 1 over x minus 0 to the first, because 0 is a, and the Taylor series is always that, x minus a to the power, and then plus 1 x minus 0 square 1 x minus 0 cube, and continue. So 1 plus x square plus x cube, which is exactly as we have for the geometric series we have earlier. That will write on page. But look like we're a little bit behind here. Right, find the Taylor series. Center at x equal to pi for the function f of x equal to sin x. I noticed that this time it is centered at pi, so it's no longer Maclaurin series. So it's going to be x minus pi as a power instead of x. Right. We need a few more terms. Right. Don't mind the phone. Nobody use the landline anymore. Let's go to 3, 4. Right. Right. So the k order derivative at a on this problem, a is equal to pi, where the center at, and we have that divided by k factorial. Right. So first, the function is sin x. X is pi. Sine of pi is 0. Oh, this did a lot more terms. So 0 divided by 1 factorial. 0 divided by 1, 0. Now we take derivative. derivative of sine x is cosine of x, and when x equal to pi, cosine pi is 1, negative 1. So take that, divide by factorial of 1, take the second derivative. Derivative of cosine is negative sine of pi. Sine pi is still 0, so still 0. Third derivative of sine is cosine, so this is negative cosine. Cosine pi is negative 1, so it is equal to 1. 1 divided by 3 factorial, 1/6. Fourth factorial, fourth derivative. Derivative of cosine is negative sine, so negative sine. Have sine of pi, again is 0. Actually, we should do a few more of this. When we put all of them together in a power series, we will have sine of x equal to 0 and then minus 1, x minus pi, because remember Taylor series is always x minus a, plus 0 x minus pi square plus 1 over 6 x minus pi cube plus 0 x minus pi to the 4th, and the next one should be minus. So notice that over 1 0, this should be 0, sorry, 0 1 2 3 4, the next one is going to be 5 factorial, and there should be 1 on top, and x minus pi to the 5th, and so on. Bottom line is we have negative x minus pi plus 1 over 3 factorial x minus pi cube minus 1 over 5 factorial x minus pi, sorry, cannot see that, pi to the 5th, and the next one, if we have to write, will be positive 1 over 7 factorial x minus pi to 7, and so on. So pretty much we have all the odd powers, because sine is an odd function, so we should have the power, an odd power. And furthermore, if we put them in the series, the first term is negative, therefore we have to have k plus 1 to have the first one to be positive, because put 0 in here, negative 1 to the 1 power is negative, so that's what we have. The first term is negative, and then we have 1 over 2k plus 1 factorial. This gives us an odd number. When k equal to 1, we have 3, k equal to 2, we have 5, and so on. Or put together have that. Right, so it's not that bad. We've been doing this a while. Notice that sometimes the center is not 0, so we have to do x minus that center instead. Right, so pretty much we do a bunch of this. It's on the big scheme of things. Just a second. I'm still here, but right. But first I go back to this one first. So we still have that is the answer. Once again, sine is an odd function, therefore we have all the odd terms, all of the terms raised to odd power. But that makes sense. And the center at pi, so we have x minus pi. Right. So on the big scheme of thing, for this section, after we do a bunch of example, we'll come up with some common series. We have that geometric series, and that those are the common function, and we have the series, and later on we just work with those series. So we should be able to go over this section rather quickly, and I even have to skip some of this because bottom line is we're trying to go to more important part, not more important part, but we just run out of time. So in that case we should be able to finish this on Monday. And even the test is up to section 11.4, but I don't think there will be any question on 11.4. So it's only up to 11.3. So basically this is kind of the last thing I put on test 3. So if you can do up to this point, I mean, if you can do up to this point, should be able to do test 3. So test 3, I'm going to plan to post that probably Saturday night or Monday morning, usually. That's why I plan. And when we have test 3 ready, I'll send you an email about all the notes, what notes you have to send back in, and try to get this done by this weekend. And the test is next Friday. The final is next Friday. So that's pretty much it. Before I close the stream, do you have any question? Only have 2 days left, so I have yes, I post the review. That will be tonight. So yes, it should be by Saturday night. You should be able to see the review. Yes, and the test 3 will be shortly after that. Yes. So that will be the review, and then 2 more videos for this, and that should be it. Yes, I have class in the usually during the day, so I can only do the review at very late night. Not sure why we need to do this. Right. So if you have no more question, I'm going to end the stream here. Have a good weekend. See you Monday.